this is a discussion of redox reactions. Redox reactions are really also called oxidation reduction reactions. They go hand in hand. What are they? Well, they are reactions in which one or more electrons are transferred so that one species gains electrons and one loses electrons. So you can remember it by this little phrase, Leo the lion says, grr. What does that mean? Leo means lose electrons, oxidation, and gain electrons is reduction. And again, this discussion is a very brief overview of oxidation reduction. When we get to electrochemistry towards the end of the year, we'll talk about oxidation reduction reactions again. But here this gives you a little bit of an overview about redox reactions and what to expect. One of the things we've talked about is oxidation state or charge of an ion. As you know, group 1A of the periodic table has a positive 1 charge, for example, and some transition elements have more than one oxidation state, and thus we would need a Roman numeral to name it. So how do we assign oxidation states? Well, the oxidation state of an atom in elemental form is 0. So if I had zinc, solid, it would have no charge at all. The oxidation state of monatomic ions equal the charge of the ion. Oxygen is -2 charge, except in peroxide. Hydrogen are +1 in covalent compounds. Fluoride, or fluorine, is -1. Of course, if it was part of a compound, it would be called fluoride. The sum of the oxidation state is always equal to 0 in a compound. And the sum of the oxidation state equals the charge of the ion in a polyatomic. So, for example, in ammonium, which is NH4 + 1, the charge of a nitrogen and the 4 hydrogens would have to equal a +1. So that's why you have to memorize those polyatomics and their charges, because the sum of those oxidation states would equal the charge of that particular polyatomic. So let's look at this particular example. These are some good questions. Find the oxidation states for each of the elements in each of the following compounds. That means we actually want to find, in the first one, potassium, chromium, and oxygen. And again, because it's a compound, they all have to add to 0. The sum of the potassium charges, the chromium charges, and the 7 oxygens have to equal 0. All right, so potassium is in group 1A. Those are always a +1 charge. And of course there's 2 of them. So I'm just going to write a 2 over here. But each potassium is a +1. Each oxygen is always a -2. Now there are 7 of them, so that means -14. So what does the chromium have to be such that it equals 0? Well, that means we have -12 here. Then chromium together has to be a +12 to make it equal to 0. But you notice there are 2 chromiums, so they have to equal +6. And let's see if we're right. Exactly. So the answer is based on the charge per atom. So chromium each has a 6. So the total is 12. But when we report the answer, we have to make sure it is per atom. All right. Now the next one, let me move this so you can see it a little bit better, is CO3 -2. It's carbonate. Oxygen is always -2. And in this case, remember, you want to make sure that they add to -2, because this is a polyatomic. So you have to think, what does the carbon have to be such that oxygen, which is -2 or -6, will work out? And you'll see that carbon has to be a 4 to make that work out. MnO2. Here is a compound that has one Mn and two O's, and again we're going to add to 0, and you will notice in this case oxygen is still -2, and in this case Mn has to be a +4 to make it work out. Next one, chlorine, and the halogens tend to be -1, so that's a -5, and so phosphorus has to be a +5. Now, that's not the most common oxidation state for phosphorus. Phosphorus is usually a -3, but in this compound, of course, it's positive, and this is how we can figure out what it is. And in the last one, SF4, fluorine is always -1, so sulfur must be a +4 to balance it out, to have a charge of 0. Now, I already told you this in an earlier slide, but redox characteristics, there is some transfer of electrons. The transfer may occur to form ions. And like I said, oxidation is losing electrons, so Leo, remember. And when something oxidizes, it increases in oxidation state, and it's called a reducing agent because it allows the other thing to be reduced. Oxidation and reduction always go hand in hand. So if something oxidizes, there must be something else that needs to be reduced. Reduction is decreasing in oxidation state, gain of electrons, remember GR, and things that are reduced are oxidizing agents. Again, if something is reduced, it's allowing another thing to be oxidized, so it's an agent for something else. All right, let's look at this. Which of the following are oxidation-reduction reactions? Identify the oxidizing agent and the reducing agent. So actually, when we identify those, the oxidizing agent is being reduced, and the reducing agent is being oxidized. We have to remember that. I always get those backwards, and I always have to say Leo GR, which means this is Leo, and this is GR. So losing electrons, something that's going to lose electrons is going to become more positively charged, and that's the reducing agent. So let's first figure out which of the following reactions are redox. So what we have to do is we have to assign charges to all of these elements, essentially, and whichever one changes is going to be a redox. This first one I can see is a redox already because here's an element has a charge of 0, and zinc in this compound, zinc chloride, has a +2 charge. So that obviously has changed. Chlorine has not changed because it's -1 and it still remains -1, and hydrogen is a +1, and here as an element, or as a diatomic molecule, it is 0. So this went from, zinc went from 0 to +2, and hydrogen went from +1 to 0. So one thing was losing electrons, and one thing was gaining electrons. Now again, if you're gaining electrons, what does that mean? If you're gaining electrons, you become more negative, and of course, hydrogen is becoming more negative, so that's being reduced. And therefore, it's the oxidizing agent. Zinc, which is going from 0 to +2, must be losing electrons. If you're losing electrons, you're actually becoming more positive, so you're becoming more positive. And that is the reducing agent. So A is definitely a redox reaction. All right. Now, looking at the next one, if you work this out, I believe this is not a redox reaction because I think the charges of these things remain the same. But the last one definitely is a redox because you can see copper is 0 charge, and it clearly has a +1 charge here. And chlorine is a -1, and this is also a -1. And copper here, you'll notice, is a +2. So copper is actually being oxidized and reduced in letter C. So let's check the answer and see which ones are oxidation reductions. Yep, and both of those happen to be redox reactions. Remember, the thing that is reducing is the agent for oxidizing, and the thing that is oxidizing is the reducing agent. And again, if you check letter B, you will see that there are no change of charge. All right, balancing oxidation reduction equations. Balance the reaction between solid zinc and aqueous hydrochloric acid to produce aqueous zinc 2 chloride and hydrogen gas. So the first thing you have to do, of course, is write the unbalanced equation, which is this one. Now notice the way that this was written. It's actually in its ionic form, its overall ionic form, which is kind of helpful, except for HCl. I'm not sure why they did that. Well, anyway, what are the oxidation states for each atom? All right, so there they are again, and hopefully you know the charges of those particular atoms. Zinc is 0, hydrogen is +1, chlorine is -1, zinc is +2 because there it is, chlorine's -1, and hydrogen gas is 0. How are electrons gained and lost? All right, so we're going to see that zinc goes to a +2. Oh, there it is. They did it for me. Let me erase my arrow. And in this case, hydrogen gained an electron, went from +1 to 0. The oxidation state of chlorine remains unchanged. So what coefficients are needed to equalize the electrons gained and lost? And essentially that's why we balance equations, is to keep, especially redox, to make sure the electrons lost equal the electrons gained. We can't just lose electrons or gain electrons. They have to be conserved. All right, so let's see what we would do. 2 are lost and 1 is gained. So to make them the same amount of gaining and losing, we'd have to multiply that first one by 2. And that's the reason we have a coefficient here. Now, I would assume that you could balance this equation without all of this, but this is how they do that. We're not fully finished yet, because what coefficients are needed to balance the remaining elements? Well, we know that the 2 has to go with HCl, and then the 2 has to go in front of Cl, because there are 2 chlorines, and there are 2 hydrogens, and 1 zinc, and so forth. So now we've not only balanced for quantity, but we've balanced for charge.